Hi, today I will speak about the pigeonhole principle. This is a very easy basic principle, but it has various uses in our various walks of life. So this principle states that suppose we have 3 urns and 4 balls. This principle says that however way we put the balls into the urns, we will have at least one urn which has more than one ball. This is shown in this example here. Now I will give you an application of the pigeonhole principle. Birthdays. Suppose we know that in a crowd there are more than 366 people. Then we can surely say that at least 2 people will have the same birthday. Another fun application of the pigeonhole theorem principle is in Delhi there are at least 2 people whose height is the same in millimeter. Now we'll move on to a problem, a quite easy problem on the pigeonhole theorem. Prove that among n plus 1 natural numbers, there must be 2 whose difference is divisible by n. The crux of this problem is that for the difference of 2 numbers to be divisible by n, each of the numbers have to have a common remainder when divided by n. Let's take the example of 37 and 25. Both when divided by 6 leave the remainder 1. Thus, when 25 is subtracted from 37, it gives 12 which is divisible by 6. Again, in 45 and 24, when we divide them by 7, we get 3 as the remainder. By subtracting them, we get 21 which is divisible by 7. Now, suppose there are n numbers. There are n plus 1 natural numbers. Now, if these numbers are divided by n, the possibilities of the remainders are 0, 1, 2 and so on till n minus 1. This gives us n number of options. Let's take an example. If any number is divided by 5, the possibilities of the remainders are 0, 1, 2, 3 and 4. This gives us 5 possibilities. Now we have the number of natural numbers as n plus 1. From the previous page we can see there are n plus 1 natural numbers. Here. So, and the possibilities of the remainders are only n. Therefore, by the pigeonhole principle we can state that at least 2 numbers will have the same remainder. This proves our statement that any the difference of any at least 2 numbers taken from this set of n plus 1 natural numbers will be divisible by n. Now let's move on to another problem, a little harder one. This is a problem from INMO. Prove that 4 points of any 5 points taken from a regular nonagon will always form a trapezium. Now let's consider 9 points. We have 9 choose 2 or 36 ways of connecting them. Now let's use Geogebra to understand this better. Now let me draw a nonagon. This is a nonagon is a regular polygon of 9 sides. Here we have a 9-sided polygon. This is quite big. I will make this a little small. Okay, so now we must realize that in this polygon, as it has odd number of sides, no side will be parallel to the other. Now we see that we can construct 3 parallel lines corresponding to each side. Suppose we take AB, then we get 3 parallel lines parallel to AB. Thus, we have a set of 4 lines including AB which are parallel to each other. Now again, considering BC, we have 3 lines again. Okay. Now, for each side of the nonagon, we can get the 3 parallel lines each, thus creating 9 sets of 4 parallel lines each. Now we have to prove that if we take any 5 points of this nonagon, at least 2 lines created by these 5 points will be from the same group. Let's move away. Okay, now suppose we choose 5 points. So the number of ways of connecting these 5 points is 5 choose 2 or 10. Now we have 10 greater than 9. Thus, by pigeonhole principle, we can state that at least 2 lines of this 10 lines formed by the 5 points will lie in the same group. Thus, these 2 lines will be parallel and form a trapezium. Let's take an example again. Let's take the point, say A, B. Let's create a new nonagon here. Here we have a nonagon, quite big one, I don't need it that big. Okay, now let's consider the points, say J, K, O, N and Q. We see that we can construct a trapezium as shown. Again, suppose we take P, R and M, L, K. P, R, M, L, K would lead to this trapezium. M, L, P, R. Thus, I have sufficiently proved that any 5 points taken from an nonagon will always form a trapezium. In this proof, I have missed out certain smaller proofs, like for example that any polygon with odd number of sides will not have any sides parallel to each other. If you want to know how to prove these points, you can always use the comment option. I will be ready to answer any of your questions. Thank you.